In this video, we're going to talk about area as it pertains to summation. When we talk about summation, we're going to be using a lot of sigma notation. And you've probably seen sigma before. It's a Greek letter. It's this guy right here. It looks kind of like a capital E. And there's a lot of things going on around it that will tell you what you need to do in order to find the sum, hence summation, of the thing it's asking you to add up. So the thing on the bottom is where I look first. So there's usually a letter here. In this case, it's I. We're going to be using I a lot. And please note that it's not the same I as imaginary number. So it's not the square root of -1. It's just a variable that we're going to be using. So that I is equal to some number, and that's our starting number. And that is called the index of summation. And a subscript I is the ith term. So normally we would say like the nth term, so however many terms you need to find is represented with that of the sum. And the upper and lower bounds are n and 1. So this number down here on the bottom is the number that you first plug in, and you plug in every integer after that up until whatever that number on top is. So if it goes from 1 to 5, you plug in 1, 2, 3, 4, and 5 and add up all those terms. And this thing right here tells you the rule. So if you're plugging in 1, you'll plug in 1 there and figure out what that term is. You'll plug in 2 into the same thing and you'll just add them up. We'll do plenty of examples, so you don't just have a rule to rely on. And something else to note, which is probably pretty obvious, is that the upper and lower bounds, so this thing on the bottom and this thing on the top, must be constant with respect to the index of summation. And also this lower bound down here doesn't have to be 1. You can start with 0, you can start with 5, you can start with 500. Doesn't matter. But n, this number on the top, has to be greater than the number on the bottom. That's all. So here are some pretty basic examples of how you can use summation and what it would look like if you wrote out all the terms in order to add them up. So for example, this guy right here is going to start with 1 and end with 6, and I is just the term that I'm going to use. So my first term I'm going to plug in 1, so that's just 1. My second term is 2, etc., all the way up to 6. And part B is an example of where you can start with 0 and end with 5, and your rule won't be I, but it'll be I plus 1, and you'll have all the same terms and you'll have the same sum. So you can write two different summations and get the same result, whatever 1 plus 2 plus 3 plus 4 plus 5 plus 6 is. And then here's some other examples where you just plug in the number and you just write out the terms, and you can add them up. You can even use your calculator. It's a handy little thing. And as with everything in mathematics, there are some handy formulas and rules that hopefully will save you a little bit of time and headache when you have summations that aren't as simple as plugging in 1, 2, 3, 4, or 5, or 6. One of them is something that we've seen before with derivatives, and that is something that's like a constant multiple rule. So no matter what your first and end values are, if you have some rule, so a sub I, so maybe that's like x squared or whatever, and you have some number outside of it, k, that's being multiplied by it. So let's say it's like 5x squared. You can remove that k and move it to the outside. So this would be 5, and then that would be your x squared. And then you would just find out whatever the summation of that x squared is, and then just multiply that end result by that k value, or if it was 5. Another thing that's really nice is the addition and subtraction properties. So let's say you have A and B, which are two different rules, and you can actually separate them. So you can just sum this A part and sum this B part separately, and either add or subtract them together depending on that rule right there. So there's some other formulas down here that hopefully will come in handy for you. This one, number 1, is telling you that C is a constant. So if that's just a number, you multiply that constant by how many terms you have to add up, and there's your answer. And then this one here has to do with that I again, which we're going to see a lot. And so if you have that number up there, n, whatever it happens to be, especially if it's a big number, this is a pattern that is created you would just plug in the n value and multiply by n plus 1 all over 2, and that will give you your summation. And that's going to be the same deal for 3 and 4. It's just a little bit more complicated because we just have I here, but this is I squared and that's I cubed. And we're going to do plenty of examples, so just hold tight for that. So let's find the sum of this expression right here. So we're going to start with 3 and end with 9, and we're going to plug it into the expression k squared plus 1. So what I'm doing here is I'm just plugging in every integer from 3 to 9 in for k, so that's 3 squared plus 1, plus 4 squared plus 1, plus 5 squared plus 1, etc., all the way up till 9 squared plus 1. So I just need to figure out what these are, add them up, and there's my sum. And so once I simplify all those terms, I just throw them into my calculator and I find the sum to be 287. So here's another example, and let's find the sum of this expression here. So we're going to start with 1 and end with 16, and our expression is 5i minus 4. So the first thing that I do here is I'm going to use that addition-subtraction rule to separate these two terms. So I'm going to sum the 5i and the 4 separately. So I'm going to pull the 5 on the outside because that's like the constant multiple, and then I'm going to figure this guy out. I'm going to use this rule in just a moment, and because this is just a constant, I just multiply 4 times 16. So what I'm going to do here is I'm going to replace this sigma with just the I with this expression in terms of n, and I'm going to multiply it by 5 because there's a 5 hanging out here. So I just do 5 times this quantity and then minus 64 because 4 times 16. And then I pulled the 2 out. It's just preference. 5 over 2, and then that's times the quantity n squared plus n, because if you distribute the n to n plus 1, that's what you get. And I will be plugging in 16 for n, much like I did up here. And the reason that I got 16 is because there are 16 terms that I would have to plug in from 1 to 16. If you counted those up, there'd be a total of 16. So let's plug in 16 again into here and see what I get. So I plug in my 16 for n, and I just simplify this expression in my calculator, and I get 616 for the sum of this guy. So let's work out another one, this time with an I squared in it. So I'm going to start my summation from 1 to 10, which will mean n is 10 terms. And let's figure out what I squared minus 1 sums to. And just like in the last example, I'm going to pull these two terms apart. So I'm going to sum I squared separately from just the negative 1, which will just be a constant rule here. And I'm going to need this rule with the I squared. So I'm going to replace this with this and figure all of it out. So let's do that. So what I'm going to do right here is replace this whole expression with this expression, this fraction with in terms of n, and I'm going to FOIL these two, distribute the n to it, so I get 2n cubed plus 3n squared plus n all over 6, and then I'm going to subtract 10 because 1 times the number of terms I have is 1 times 10, so that's subtracting 10, and I'm going to plug in 10 every place that there's an n here. I do that, and I end up with 375 as the sum of this expression. Let's do one last example, but this time it's in terms of n at the top. So my expression is I plus 1 all over n squared, and we're going to be asked to plug in 4 different values for n, so 10, 100, 1,000, and 10,000. So what I'm going to aim to do is look back to those formulas, those rules that I had, and see if I can't break this up into a way where I can just simply plug in an n or 2 and plug in 10, 100, etc. So my goal for this process was to get I by itself, because if I look back to the formulas that I don't have anything that is I plus 1 or anything over n squared, so I have to isolate that I, because I do happen to have an equation for that, and it is right here, which we'll use in a moment. So what I did is I realized that this quantity can be written like this. So 1 over n squared times the quantity of I plus 1. So I just separated the numerator and the denominator and made them separate. And so this is being multiplied, which means that I can bring it to the front, because remember, n is just some number that we're going to plug in 4. So that means that this is just a constant in the end. And so now I'm left with the quantity I plus 1 behind the summation. And we've seen this before. We can separate the I and the 1 into their own summations. And then from here, I've got my I by itself, which means that I can plug in this thing in terms of n and figure out the rest. And I plug in this expression in terms of n for the summation of just I, which is great. So the summation of 1 times however many terms that I have, so that's n number of terms, which remember is just a number, so it'll be 10, 100, etc. So I'm going to distribute my n to my n plus 1, so that's n squared plus n, and that's all over 2. And what I did here to get the 2n is I have an n here, and if I want it to share a numerator, I need to multiply that by 2, so 2n over 2 gives you n. And then I'm going to distribute my 1 over n squared to this quantity, which just makes 2n squared in the denominator. So one step away from simplifying this. They all have an n in common. I take it out, so I'm left with n plus 3 over 2n. And what that enables me to do is plug in any value for n, whether it's 10, 100, 1,000, or 10,000. So here's a nice little handy-dandy chart that is so much better than my handwriting. And when you plug in values for n, so whether that's 10, 100, etc., you'll get these solutions here. And something that you may or may not notice when you do that, so for 10 we get 0.65, for 100 we get 0.515, for 1,000 we get 0.5015, and then for 10,000 we get 0.50015. And if you want to see where this thing goes as it approaches infinity, which will tell you the limit as that number approaches infinity, you can apply the limit process to this like we did last chapter, and we end up with 1/2, which is kind of what we're getting right here. So that will lead us somewhere. But that's all we're going to cover in this video. So thanks for watching.